The final topic in the limits and continuity unit is called the Intermediate Value Theorem. Now, the Intermediate Value Theorem is a very key concept in calculus if you're going through improving all of the details in great detail. Because we can have a casual appreciation that something is probably true, but functions can get weird. Continuous functions even can be weird. You saw in the last video that I showed you the graph of y equals sine of 1 over x. And that function near 0 just looked like a rectangle of ink. And so that's the kind of thing that functions can do and still be continuous. And so when you go through and look at all the details, you look at weird functions like that and make sure that even those satisfy the rules that we set. But the first time through calculus, we're allowed to take these major details on faith. So let's take advantage of that. At the same time, you will see questions on tests that will ask you to apply a knowledge of the intermediate value theorem. So we're going to look at what the intermediate value theorem is, and then we're going to look at what those questions you will see will look like and how to think about answering them. All right, so we're going to start out with my paper. All right, so the intermediate value theorem. So let's imagine a function on this graph, and the function is continuous. So I'm drawing it with a single swoop of my pen, and it's kind of just doing this kind of thing. All right. And so here's what the intermediate value theorem says. It says that if we've got one value and we've got another value, so let's think about what the y values are at these two functions. All right, so what the intermediate value theorem says is that for any output value in this range between the output of the left-hand side and the output of the right-hand side, there must be some value of the input that matches it. Okay, let me give you an example. So if I said, all right, so here, let's say that f of 2 is equal to 7, and I'm going to say that f of 5 is equal to, that's a negative number, so let's call that -7. All right, so is there some value of c such that f of c is equal to 0, where c is between 2 and 5? Does that exist? And the intermediate value theorem says as long as we know that this function is continuous between these 2 points, I'm drawing it with a single stroke of my pen or my pencil, then the answer is yes. And so casually we can think about it like this, that we can use kind of the horizontal line test, if you can remember that from Algebra 1. So I've got my pencil here where the output value is 0. And so since the function starts above the pencil and ends below the pencil, is there some place, does there have to be some place where the function crosses that pencil? And the answer casually is, yeah, it would have to be, because we're drawing this with a single stroke of the pen. So we're going above, above, below, below, below. There's some point that we had to cross that line. Okay. Now you have to know that the function is continuous. So for instance, if we had a function that looked like this, so I had a function that was doing this thing, and then it had an open circle and a closed circle, and then it goes and does this thing. Then between here and here, the value of the function goes from being positive to being negative, but there is no point in that interval where the output is exactly equal to 0. And that's because the function isn't continuous here. All right. But if the function is continuous, then yes. And you can see that outside of this range, we really can't say anything. Okay, if we think about this horizontal line up here, it turns out that yes, there are some values of the function that cross the line up here. but up here there is no such line. So the intermediate value theorem only talks about the range between the left-hand output value and the right-hand output value. All right, so what I want to do now is I want to take a look at an IXL that's quizzing us on this unit or on this skill, and we will see exactly the kind of questions that you can get. They're a simple enough concept that I don't really want to assign this IXL to you. I just want you to watch this video and kind of appreciate what's happening. All right, so here's the kind of question that you can get. The function k of x is continuous on this interval where the input ranges from -13 to -7. All right, so if k of -13, that's one of my sides of that interval, is 10, and the other output is -2, can you conclude that k of x is ever equal to 0? All right, so the output of the value ranges continuously from 10 to -2, does it have to cross 0? And the answer is yes, it does, because 0 is between 10 and -2. All right, so because it's in that output range and the function is continuous, that's a very important detail that we need to know. That is enough information because of the intermediate value theorem for us to conclude that k of x has to be 0 for some x between -13 and -7. All right, the function g of x is continuous on the interval from 7 to 12. If g of 7 is 7 and g of 12 is 10, can you conclude that g of x is ever equal to 0? So pause the video and give this a moment's thought if you need to. Well, this time, the output values over the endpoints of our interval range from 7 to 10. So we can be absolutely sure that there is some value in that interval where the output value is 8 or 8.1 or 9.997 or anything like that. But only the numbers between 7 and 10 are things that we can be confident about. So 0, maybe, maybe not. We cannot conclude that with certainty because 0 is not in that interval between 7 and 10. All right, so the answer to this is no. Now the function q of x is a polynomial. So this isn't directly telling you that the function is continuous, but one thing to remember is that all of the functions that we're used to dealing with are continuous. All right, so polynomials are always continuous. Exponential and logarithm functions are continuous. Sine and cosine based functions are continuous. The rational functions that we've been thinking about while we've been doing limits, those are continuous everywhere except where the denominator is equal to 0. So any point other than that, the function is continuous there. So knowing that this function is a polynomial is enough for us to conclude that it's continuous. So if q of 2 is -1 and q of 9 is -3, can you conclude that q of x is ever equal to 0? Well, this time the outputs that we can be confident about because of the intermediate value theorem is between -1 and -3. So 0 is not in that range. So we cannot be sure that q of x is ever equal to 0. This could be a polynomial that's negative everywhere. Okay, you can imagine a quadratic function that only goes as high as -1. So that function is continuous, it's a polynomial, but it never has a value equal to 0. All right, and the function f of x is continuous on the interval 5, 12. I'm going to let you read these. I'm just going to take a few seconds and then I'm going to answer them. So this time, our range of values we're sure about goes between 9 and 3. So 0 is not in that interval, so I can't be sure that there's ever a value that does. Some functions will go outside that range, but you can't be confident that it will. All right, in this function, the output values along our endpoints go from 3 to -10. Is -3 inside that interval? Yes, it is. So we can be sure that there is some input value somewhere between -1 and 4 that satisfies f of c is equal to -3. I don't know where it is. It depends on what the function looks like. But I know there has to exist one. And this will be the last one we look at. Okay, once again, polynomials are always continuous, and the output ranges from 3 to -3. 0 is in that range, so we can conclude that there must be some output value that's equal to 0. All right, and that got us up to 1 metal, which this IXL doesn't get any harder than this. So the idea of the intermediate value theorem is kind of intuitive, I think. And you can see that the questions that they ask about it aren't particularly hard. But you need to be able to recognize that problem type and go, oh, this is an application of the intermediate value theorem. And make sure that you're told that the function is continuous, because that's a key idea. As we saw in one of the graphs on the paper, when the function is not necessarily continuous, it doesn't need to meet all of those intermediate values between the two output values. All right, so that is the last topic in limits and continuity, and I'm going to make one video just kind of encapsulating the whole unit that we did.